The objective of this video is to introduce graphical visualization and operational techniques for transfer functions using Bode plots. Operational techniques will include the negation, inversion, scaling, multiplication, addition, and parallel operation of transfer functions. So specifically, we're going to be talking about techniques to visualize the frequency response of a circuit in terms of its magnitude and phase angle. And this is an important topic for two reasons. First is that design specifications will limit or dictate the performance of your converter. This may be in terms of voltage and current ripple, and we've previously calculated this by using L didt and C dV dt. But now we want to consider this in a more general sense. And when we use the differential equations for the inductor and the capacitor, we had considered rather simplistic waveforms and simple circuit operating conditions, or simple circuits as well. Now we want to consider a more general case. We may have many inductors and capacitors in parallel or series, or we may have some rather arbitrary waveforms. But the second and perhaps much more important reason for studying the frequency response of a circuit is to prevent instability when we design our regulators. We need to be able to not only guarantee the regulator's closed-loop performance, but we also need to make sure that it is always stable for any input conditions. And as you'll see as we develop this, it's going to become particularly important to study the phase angle of our circuit when the gain of our circuit is 1. So we might be considering as an input our duty ratio and as our output our voltage or our current, and we're talking about the relative gain from duty ratio to our output voltage or current, or the phase angle from our duty ratio to our output voltage or current. Previously, we've talked about transfer functions in terms of converting one voltage to another voltage, or a voltage to a current. And we've also talked about how to write transfer functions in terms of poles and zeros, how to classify these poles as zeros as being left half plane, right half plane, simple, and how to identify poles and zeros. We've specifically talked about regular poles and zeros as well as inverted poles and zeros. And now we're going to start to talk about how to visualize our transfer functions in the frequency domain. So you can already go to MATLAB and you can tell MATLAB where your poles and zeros are, and it can create a frequency response plot for you. However, this frequency response plot will not help you design your circuit. It doesn't give you any physical intuition for what features of the frequency response were created by what aspects of your circuit. So if you specifically want to add a gain in some location or change the phase delay in another location at a different frequency, you won't know what circuit elements you should be modifying, adding, or removing. The objective of this video and this unit is to create physical insight, to build physical insight into why our system behaves the way it does, so that we're actually able to design a system. When it comes to regulator design, which we'll be talking about in future videos, we're going to want to obtain a certain transfer function. We'll know how much gain we want at what frequency and what our phase delay should be at another frequency. And we want to be able to actually pick out circuit elements that will realize this transfer function. So what we're going to be doing is we're going to be talking about a simple technique to visualize a transfer function, which is referred to as a Bode plot. This technique is named after its inventor, who is Henry Bode, and he invented this while he was at Bell Labs in 1938. So the Bode plot is a visualization technique for transfer functions. It's actually one of several visualization techniques that include the Nyquist plots and Rit-Locus plots. And all of these techniques can be used to get you to the same place. They can all be used to visualize the transfer function to create physical meaning for why the transfer function is the way it is and for why the system behaves the way it does. They can all be used for studying stability and performance of a closed-loop system. In this class, we're going to be studying the Bode plot exclusively. So what is a Bode plot? Well, the defining characteristics are as follows. It has an x-axis, which is logarithmic, and is in units of hertz. And then it actually consists of two plots, so it has two y-axes. So these plots are intended to show the magnitude and phase of our transfer function. And as we develop this, I want you to keep in mind what a transfer function is. It's relating an output quantity to an input quantity. So as we've talked about in our previous videos, we've considered an output as being a voltage and an input as being our input voltage. And so when the transfer function is evaluated in terms of its magnitude and phase, which is what we're about to plot in our Bode plot, we're talking about the gain of the transfer function for the magnitude, so that is how much V out is increased over V in at a specific frequency. And we're talking about the phase between the signals, so what the phase of V out is relative to the phase of V in. So if you give me a transfer function and you evaluate it at a frequency of 1 kilohertz and you tell me it has a magnitude of 2, that means that its output voltage is going to be twice as large as its input voltage at 2 kilohertz. And if you tell me it has a phase angle of 15 degrees, that means its output voltage is going to lead the input voltage by 15 degrees. So remember that we're talking about sinusoidal quantities here. We're talking about a sinusoidal input voltage yielding a sinusoidal output voltage at a specific frequency. Now, back to our plot with its two y-axes. The first axis is to represent the magnitude of the plot. And as we talked about last time, magnitude is going to be in units of decibels. So we calculate this using the expression 20 times the log of the magnitude of our frequency response transfer function. When we plot this, we're going to label the y-axes in units of 20 decibel increments. And 20 decibels corresponds to a multiplication of 10 times. The second y-axis is going to be a representation of our phase angle between our input and output signals. And this is going to be in units of degrees. And so we'll label this y-axis in units of 45-degree increments. And we'll plot it over the range of negative 180 degrees to positive 180 degrees, which gives us a full 360-degree representation. So let's now sketch a Bode plot. And so you can see that I've already labeled for us the frequency range as starting at 0.1 hertz and going up to a megahertz. Every tick on this x-axis represents a multiplication of 10. So we start at 0.1 hertz, and then we go up to 1 hertz, and then 10 hertz, 100 hertz, a kilohertz, 10 kilohertz, 100 kilohertz, and finally a megahertz. And we could keep continuing. We could continue this on towards gigahertz and terahertz and so on and so forth. But the interesting detail here is that this is a logarithmic scale, which enables us to represent a very broad frequency range. So on this one plot is everything from a fraction of a hertz up to a megahertz. And while representing this very broad frequency range, we retain our ability to discern small changes in frequency. So at the 1 hertz and 0.1 hertz scale, at the low frequency regime, we're able to make out differences in frequency as low as 0.1 hertz, while still being able to present data at very large frequencies. In this case, we're showing up to a megahertz. So this is a key feature of a Bode plot, is that the x-axis is in a logarithmic scale and is labeled in units of hertz. Our y-axis, again, I said we have two axes, and the first one, or the top one, is the decibel representation of the gain of our transfer function. And again, we're going in 20-degree increments. So to illustrate what this means, we can write to the left of this what the magnitude of our transfer function would be in order to obtain these 20-degree increments. So 20 times the log of 1 is equal to 0 decibels. 20 times the log of 10 is equal to 20 decibels. 20 times the log of 100 is equal to 40 decibels. 1,000 is 60 decibels. Each tick is a multiple of 10. This ends up being a log-log plot if we were indicating our y-axis as simply the absolute value of j omega. But instead we're indicating our y-axis in decibels, which makes this a semi-log plot. Going down from 0 decibels, we can see that 20 times log of 0.1 is negative 20 decibels. then 0.01, 0.001, and so on and so forth. We could extend the decibel range upwards and downwards from here. A couple key things to note about the y-axis and x-axis as labeled so far. For the x-axis, realize that we can't ever plot 0 Hz. Every tick mark represents dividing our frequency by 10 as we go downwards. So the next tick below 0.1 Hz would be 0.01, and then 0.001, and then 0.0001, and so on and so forth, but we would never actually get to 0 Hz. The second interesting detail here is on the y-axis on the top. We actually can never get to a gain of 0. 0 decibels corresponds to a unity gain, corresponds to the magnitude of g of j omega being 1. But if g of j omega is equal to 0, 20 times the log of 0 is actually negative infinity. So we can only represent it as an asymptote. Now for our second y-axis, we consider the phase angle between our transfer functions. And as I said, we can plot this over the range of 180 degrees to negative 180 degrees. So we now have our complete Bode plot axes drawn, and we're going to sketch example Bode plots on these progressively as we go through this video. But before we do that, let's just remark back upon the defining characteristics of a Bode plot. And that is that the Bode plot has a single x-axis, which is in units of hertz and is on a logarithmic scale, and then it has two vertically aligned y-axis plots, one for magnitude and one for phase. The magnitude plot is in units of decibel and in 20-degree increments. The phase angle plot is in units of degrees in 45-degree increments and goes from negative 180 degrees to positive 180 degrees. So if the plot does not embody all of these characteristics, it is not a Bode plot. You can make frequency response plots in MATLAB easily that are not in units of decibels or are not on logarithmic scales, and these are not Bode plots. For the purposes of this class, a Bode plot has to have all of these characteristics. Let's start with a rather simple example. Suppose that we have this very simple circuit, which consists simply of a resistor. It has an input current of I and an input voltage of V. And what we're going to do is calculate the frequency response transfer function between V and I. So we'll call this our transfer functions G, and it happens to be equal to the impedance, which is our voltage divided by our current. And we can see that it's simply equal to the resistance. And suppose that that resistance is 10 ohms. How would we plot the Bode plot of this? Well, 20 times the log of the absolute value of 10 is equal to 20 decibels. So we would see that we have a constant magnitude gain at 20 decibels. And we'd have an angle which is equal to 0 degrees. So we now have a Bode plot depicting the frequency response of our very simple transfer function. And it's a pretty boring Bode plot. We've got a constant magnitude and a constant phase angle. Suppose now that we were to change the definition of current in our circuit. Suppose that we had a circuit that looked like this instead, where current is now flowing right to left. We would say that our transfer function is equal to a negative R, which is a negative 10 ohms. So what does that do to our Bode plot? Well, the magnitude is calculated as an absolute value. So the absolute value of a negative 10 ohms is still going to be equal to 20 decibels. Our magnitude stays the same. Our argument, on the other hand, our angle of negative 10 ohms, is now going to be a negative 180 degrees. So our phase plot ends up looking like this. And this operation right here corresponded to a negation. So we said at the beginning of this video that we're going to consider operational techniques. So we want to be able to negate, invert, scale, multiply, add, and parallel transfer functions. And we just checked off our first one. We show what happens when you negate a transfer function. That is, the magnitude remains the same, but its phase angle is 180 degrees different. And these operational techniques are going to save us a lot of time further on in the course. The idea of this is that instead of having to rederive our transfer function from scratch, we can just recognize that we've changed an aspect of our transfer function. We've multiplied it by another transfer function, or we've negated it, and then quickly see how to change our Bode plot to reflect this. So our first operational technique was negation. Now, to give us a little bit more to work with, I'm going to add a second transfer function that we'll plot up here. So in addition to this simple resistive circuit, let's also consider an inductive circuit. And now our transfer function is equal to S times L. If we were to, for convenience, select L equal to 1 by 2 pi Henry, then we can say that G of j omega L, which is in turn equal to j 2 pi f times 1 by 2 pi, and that ends up being jf. So we've intelligently chosen L to be 1 over 2 pi to get a convenient function here for plotting. And therefore, we can see that the magnitude of our transfer function is always going to be 20 times the log of f, and the angle, or the argument, of our transfer function is always going to be equal to 90 degrees because of that j. So we can plot this on our axes, and we'll use red. So at f equal to 1, 20 times the log of 1 is 0 decibels. And at f equal to 0.1, 20 times the log of 0.1 is equal to negative 20 decibels. We end up with a straight line, and this is decibels of. Meanwhile, our phase is always down here at negative 90 degrees. So we now have a Bode plot which shows two individual transfer functions. One of the transfer functions is R equal to 10 ohms, and the other transfer function is L times S, which is equal to J times our frequency. And let's do some color coding here for clarity. So we've said that red is going to be our new transfer function, which is the transfer function of the inductance. So that's this guy down here. And on this plot, we've made orange be our simple resistor circuit, which is this transfer function up here. We're going to keep adding onto this plot as we progressively go through the rest of these operational techniques. So we've done negation. Now we're going to do inversion. And we'll just keep working our way down on this sheet. So inversion, by definition, is 1 over a transfer function. So our new transfer function is equal to 1 over our old transfer function, or the reciprocal. So if we calculate the magnitude of this in decibels, we have 20 times the log of 1 over our old transfer function. And the properties of a logarithm tell us that this is just simply going to be equal to a negative 20 times our old transfer function magnitude in decibels. So this is a property of a logarithm, and we can immediately conclude that the magnitude is reflected. The decibel magnitude is reflected So this is one of the reasons that we choose to plot our magnitude in decibels, so that we can take advantage of this property. The second thing that we can observe when we consider our phase angle is that if our old transfer function was written in the form of a magnitude and an angle, such as this, we can immediately see that our new transfer function, which is 1 over g0, is going to be equal to 1 over m e to the j theta, which is equal to 1 over m times e to the negative j theta. So we can conclude that in this case, our phase is reflected as well. So we've got two conclusions here. And let's practice this for the case of our inductor. Let's now make a plot, and we'll color code this again. So we'll say that in this case, g of j omega is equal to 1 over SL, where we're using our previously defined transfer function for SL as being 1 over 2 pi. L is 1 over 2 pi. And we can do this by going back to our Bode plot and now reflecting our magnitude plot about the axis, taking the negative of it, which is going to look like this. And so this was decibels of 1 over LS. And similarly, we can go to our phase angle plot and see that we're just going to have a straight line going across. So we were able to do this without having to go back and reconsider the exact form of our transfer function. We're just able to recognize that we've already plotted the transfer function. We've already made the Bode plot for the transfer function LS, and so therefore we know how to create the Bode plot for the transfer function of 1 over LS. The next property that we're going to discuss, the next operational technique, is multiplication and scaling. So we're going to do this in one shot. So if you go up to the top, we had said scaling and multiplication. Now we'll do this together as one item, because scaling is a simpler form of multiplication. And scaling and multiplication means that we have a transfer function which consists of the multiplication of two existing transfer functions. So in this case, we'll say it's g1 of s and g2 of s. So if we look at the magnitude of this, we're taking 20 times the log. And we go back to the properties of logarithms again. This is simply equal to the summation of the two transfer functions. So yet again, our choice of plotting in decibel magnitudes is paid off, because now multiplication operations are simple summations. And we can talk about the phase angle as noting that if we were to express each transfer function in complex notation, we would add their arguments. So the decibel magnitudes add, and so do the phase angles. So let's consider an example of a new transfer function, which is going to be equal to our resistance times our inductance. So G1 of S is equal to our resistor transfer function, and G2 of S is equal to our inductor impedance. So we go back up to our Bode plots, and we can see that we're going to add the red and the orange lines, which is effectively going to shift the red line over by 20 decibels. So the red line, instead of crossing at at 1 hertz is now going to cross at 0.1 hertz, and it's going to have the same slope as before. And so this is decibels of RLS. And our phase angle is going to be the red line added to the orange line, which is going to remain at negative 90 decibels. So in this case, because our resistive transfer function was constant magnitude, the only change is that we shifted our gain by 20 decibels. We shifted it to the left by 1 decade. However, if we'd had a more complicated transfer function for the first transfer function, so this is produced by multiplying a G1 times a G2, if G1 was more complicated, we might have actually changed the slope of this line, and we might have changed the phase angle down here as well. But the point is that you add the results of the two transfer functions. So you can, again, construct this entirely by looking at your Bode plot without having to actually work through the math and the algebra of your new transfer function. Okay, so we've done negation, we've done inversion, we've done scaling and multiplication. Let's now do addition. And so addition is saying that g of s is now equal to g1 of s plus g2 of s. And this is one way that you can view a pole or a zero from our last video. So in our last video we had said that a pole or a zero was the transfer function of 1 plus s over omega 1, either in the denominator for a pole or in the numerator for a zero. And you can see that this is the sum of the transfer function 1 plus the transfer function s by omega 1. So this is an important case for us to consider. It's going to become fundamental for us plotting Bode plots, ultimately, is that we'll be looking at things in terms of poles and zeros. So, for example, we could consider this to be the summation of our resistor plus our inductance. So you can imagine that you can easily have this circuit where you might have started off with just having this simple circuit right here, V old, going into I old, and now you're going to add this resistor, and so you're going to get a new, more complicated system. And in this case, what we do is that we're going to make an approximation. In our other three operational techniques, we were considering exact operations. Now we're going to make an approximation, and our approximation is going to be that the decibel magnitude is equal to the max of G1 and G2 for any frequency. So in other words, what we're saying is that if the transfer function of R is really large compared to the gain of j omega times L, we're going to approximate this circuit as being purely a resistance. Or if the transfer function of omega L is really large compared to R, we'll consider it to be purely resistance. And so this depends on the frequency that we're at. This either is going to look like a resistance, or it's going to look like an inductance. And then when we're in an intermediate frequency range, it looks like some combination of both. And so this is an approximation. And then what we're going to do for our phase angle, which is again an approximation, we're going to say that this is the average. Well, we're going to note something first here. When G1, the frequency that the G1 magnitude is equal to the G2 magnitude, so in this case right here, if G of S is equal to R plus J omega L, when this is equal to this, we have if they're both equal to 1, for example, we have 1 plus J1. We can easily see that at this frequency, the argument of G is equal to 45 degrees. So in that instant, that means that we had a resistance along the real axis, and we have j omega L along the imaginary axis, and if they're at equal magnitude, our total impedance has an angle of 45 degrees. So our approximation is going to be a piecewise linear function. It's going to say that at the frequency where g1 equals g2, we're going to take the average angle of these two transfer functions. When for the frequency where g1 equals g2. So we have three cases. The other case is that when g1 is much, much larger than g2, so we're going to say 1 decade lower, we're going to take the angle as being the argument of g1. So the angle of g1. And we're going to approximate being the angle of g2 1 decade of frequency higher. 1 frequency decade higher. And in between, it's going to be a linear approximation. So this is our phase angle approximation and our decibel magnitude approximation above. All right, let's recap this. The decibel magnitude approximation is that we're always going to take the maximum magnitude of g1 and g2. And the phase angle approximation is that when we are 1 decade or lower below the crossover point, we're taking the argument of g1. And when we are 1 frequency decade higher than the crossover point, we're going to take the angle g2. And in between will be a linear approximation. So let's show what this looks like. We're going to, in this case, we're going to, well, let's see here. Let's use, we'll use the color brown to show this example. We're doing R plus SL. So you go back to our Bode plot, and we're going to take the maximum of the orange line and the red line. So the Bode plot for this transfer function is going to be along here and then up to here. So you can see at these really high frequencies, we look purely like an inductance. And then at the low frequencies, we look purely like a resistance. At the point where these two, where we have this inflection point right here, we're going to have that be the phase angle is going to be the average of the phase angles of these two lines. So the average of the phase angle of the red line and the orange line, which is going to be 45 degrees. So at 10 hertz, we're at 45 degrees. 1 decade lower, and we're completely on the orange line, which is 0. 1 decade higher, and we're completely on the red line, which is negative 90 degrees. So our phase angle is going to look like this. And remember, this is an approximation. So let's label this. The final operation that we're going to consider is parallel operation. So we've talked about negation, inversion, scaling, multiplication, addition, and now parallel operation. And parallel operation is again going to be an approximation. So if we parallel two transfer functions, we might be, for example, talking about placing a resistor in parallel with an inductor and talking about our voltage-current relationship again. So paralleling two transfer functions means that we have a new transfer function, which is the parallel combination of our two previous transfer functions. So for example, what we're actually going to end up sketching, and I'm running out of colors here, we'll do this seafoam green. And the approximation is that the decibel magnitude will now be equal to the minimum of G1 and G2. And this makes sense. This is saying that if R is much, much less than J omega L, that this circuit is effectively going to look like a resistor. But if J omega L is much, much less than R, this circuit is going to effectively look like an inductor. And we know this intuitively from our classes in circuits, that if you have two parallel components and one component is much, much smaller than the other one, the impedance ends up looking like the smallest component, approximately. The second is that we're going to approximate our phase angle using the same techniques as we used for the addition as number 4. So let's give this a try. We'll get back to this funky seafoam green. We're going to consider R in parallel with SL. So now the decibel magnitude is going to be the minimum of our orange and red lines. So we're going to track this path here. And likewise at this 45, likewise at 10 hertz, where we have this inflection point, we're going to say that our phase is the average of those two quantities, which is again going to be 45 degrees. Only now we're going to be going from negative 90, because at low frequencies the inductor was the lowest impedance. We're going to be going from negative 90 up to 0 degrees. Okay, so that wraps up each of the operational techniques. We're going to be practicing this in class in some active learning exercises, but I want to conclude by pointing something out to you. In a previous active learning exercise, I had you calculate the parallel combination of R with SL, and I asked you to so you calculated this as presumably something like the following, and then I asked you to put this into an inverted pole form, which you factored to be this expression. So notice that we did the same thing in this example right here, only we took a shortcut. We already knew our transfer function for R, we already knew the Bode plot for R, and we already knew the Bode plot for SL, and so we were able to use this operational technique to quickly combine these Bode plots and get our final frequency response for the complete system. So this is something that you're going to get plenty of practice of with our class, and it's going to be an important tool that we know how to take two different transfer functions and combine them in order to get a final transfer function, and this gives us physical insight and meaning into our system along the way. It prepares us for being able to design our own transfer functions. So if you know that you want a certain Bode plot for your system, you're building up the physical intuition to be able to say, hey, I need to add a resistor and an inductor in order to make this Bode plot real, or I need to add a capacitor over there, or I need to add another parallel branch.